Check 1, 2, check. One, two, one. Check, check. Check 1, 2, check.
For those on the internet, regarding our seminar, we're just slightly delayed because of technical difficulties, but we should be getting going in, I would say, 5 minutes. Thank you.
Check 1, 2. Just like check, check. So we'll get you going. Check 1, 2, check.
Good afternoon. Welcome to today's seminar. Before we do start, though, we'd like to be sure that you're aware that in case we need to leave the room for an emergency, we have our exit signs surrounding us, and be aware where they are. Also, for those that are on the internet, we strongly encourage you for the Q&A to send your questions to the address on the monitor at first opportunity, so we could have time to take it during the Q&A period. So with that, Sarah?
Oh, do you want to? Sorry, I thought you did it from there. Well, good afternoon. Good afternoon, everyone, and thank you for coming today. Today's seminar is on mitigation of nitrous oxide emissions from agricultural soil management. To better help you understand the context of this project, I'd like to provide some background on ARB's research program on nitrous oxide emissions from agricultural soils. Lei is actually the contract manager for these projects, but she had a family emergency and had to leave for China last week. So unfortunately, she couldn't be here today, so I'm giving the introductory presentation. As I'm sure you know, nitrous oxide is a potent greenhouse gas. It's long-lived. It has a high global warming potential. According to the 2013 California Greenhouse Gas Inventory, nitrous oxide contributes about 3% of the state total emissions, and about 2/3 of which came from the agricultural sector. So used to having someone else switch the slides. N2O emissions have a high spatial and temporal variability. Nitrous oxide is a byproduct of microbial activities in the soil. All the factors affecting microbial activities have an effect on N2O emissions from soils. N2O is produced from anaerobic denitrification and aerobic nitrification, and I'm not going to get into the complexities of the nitrogen cycle, but Martin will be talking about that later, and you'll learn all about leaky pipes. The regulating factors that affect N2O emissions include agricultural practices, which are really linked to the availability of nitrogen, soil conditions, so the availability of carbon and nitrogen that feed the microbes that make the nitrous oxide, and then soil texture and soil moisture are going to affect the amount of oxygen in the soil, which provides the right or wrong environment for nitrous oxide to be produced. And then also, climate, because microbial processes are driven by higher temperatures, and precipitation, which is obviously going to affect soil moisture. Oh, yeah. So this is a figure showing the variability of N2O emission rates from agricultural fields around the world. And nitrous oxide emissions are highly variable because they're affected by so many environmental factors, which obviously vary across the world. The correlation between nitrogen inputs and nitrous oxide emissions is weak when data is from different places around the world and from different crops, which really calls out the need for California-specific emission factors. The line that you see is the IPC default emission factor of 1%. And this is what we use in the California emissions inventory. The yellow symbols are California data. So the high emission rates that you see around 600 are from Santa Barbara vegetable plots, and the lower emission rates around 300 are from Yolo County from uncropped plots. The emission rates there range from 0.3 to 3%, whereas the higher emission rates were 10 to 30% of nitrogen application. This diagram I just included because it really illustrates the complexity of nitrous oxide emissions and shows the interplay between here just rainfall and management practices that have large impacts on N2O emissions, and it just really calls into account, I listed all those variables that impact nitrous oxide emissions before, but they are all interplay with each other. So as you can see on the left side of the graph, the rainfall did not have a lot of impact on N2O emissions, but then when you have management practices that introduce nitrogen, such as fertilization, or if you have tilling, then with rain you get these high peaks of nitrous oxide. And then there's high spatial variability from the microscale to the regional scale with coefficients of variation from 50 to 200%. At the less than 1 meter squared scale, variation is linked to the presence of anaerobic denitrifying microsites in the soil, but at a scale of larger than 1 meter squared, variability is often linked to mineral nitrogen availability or to topographic effects associated with poor drainage that lead to high emissions. So you can have hotspots which emit at rates several orders of magnitude above the background N2O fluxes. So I'm just including these diagrams to illustrate the difficulty in modeling N2O emissions. And so the motivation behind the N2O research that we started in 2008 was driven by AB 32 and the state's goals to reduce greenhouse gas emissions. And then one of the early actions identified in the initial scoping plan was to conduct collaborative research to understand how to reduce greenhouse gas emissions from nitrogen land application. And then, of course, there's limited field observations in California, which are important because we have unique soils, we have unique crops like almond specialty crops, and we have unique management practices. And then there are discrepancies between studies that have done emission inventories from top-down and bottom-up methods, and N2O emissions from atmospheric measurements and modeling are 1.3 to 2.3 times the California inventory. Did the volume just go up, or is it just me? Okay. This gap is likely from natural sources, but we need to ensure that anthropogenic sources are accurately identified in the California inventory. And then the objectives of the research program are to improve the emission estimates of N2O for California agriculture, to identify mitigation options, to reduce emissions from soils, and also to track progress and verify the assumed reductions over time. In order to leverage resources around the state and avoid duplication of efforts, since there were several research entities that were interested in this work, we coordinated with other research entities like state agencies such as CDFA and the Energy Commission and CalRecycle. We also coordinated with the Packard Foundation and the USDA. And together, we devoted about $3 million to N2O research starting in 2008. And all of our research activities were overseen by the N2O Working Group, which was a subgroup of the San Joaquin Valley Ag Tech Committee, which has a broader group of agricultural stakeholders. But these groups consist of stakeholders from industry, local, state, and federal government agencies, academia, and environmental groups. We hold periodic meetings to discuss research priorities or any technical issues and share progress. So I'm not going to go over every project in this timeline, and there are printed handouts, and this presentation is available online as a PDF, but I'm just showing you a Gantt chart of the projects that we've funded over time. So these are just the ARB projects. They don't include the other projects from the other research entities that I said that we coordinated with. I just want to call out a couple of the projects. Starting in 2011, we had this atmospheric measurements of GHG and inverse modeling emissions. And that was coupled with the Blue project called Data Analysis of Regional Greenhouse Gas Emissions, also starting in 2011. So we were working in-house and with external researchers to measure nitrous oxide emissions from towers, and then in-house using the mobile monitoring platform and chamber studies. But we started measuring nitrous oxide at Mount Wilson, which is in our tower network, in the spring of 2012, and recently began measuring it at the Walnut Grove Tower, and I'll talk more about those later. And then I just want to also point out that we study more than just agricultural N2O emission studies. We are also studying emissions from motor vehicles. So the very last project on the Gantt chart shows this N2O emissions work we're doing from motor vehicles, and that's being done in-house. We're doing on-road emission measurements with the mobile monitoring platform, also taking measurements from parking garages and in the Caldecott Tunnel to inform internal mobile source teams in the ARB. But the ag baseline and mitigation field studies have been completed. We've nearing development of the modeling tool, and emission verification inventory development is ongoing. So I'm going to talk a little bit more about the methods that we use. So this is a picture of the Walnut Grove Tower. It's kind of hard to see, but it's on the left of the text box that says Walnut Grove Tower. And we're taking N2O measurements there. The ambient monitoring program monitors N2O concentrations among other gases in the atmosphere to convert the measured concentrations to fluxes by using inverse modeling that we do in-house, thereby providing a top-down approach to verify or track emission trends. And then we're also contracting, and we have chambers that we can use in-house to study emissions just right in the field, which have been really useful. And then this is a picture of our mobile monitoring platform that has instrumentation to measure greenhouse gas emissions as it drives around. And the mobile monitoring platform can complement the aerial measurements that we take. So this is a picture of a flight pattern that that plane took under the CalNex study to measure N2O and methane emissions over the rice fields in California. But we are partnering with JPL, and we will continue to take aerial measurements. They're taking grab samples, and we will coordinate JPL's efforts with our in-house mobile monitoring measurements. So the studies that we've done included 9 of the top 10 crops with the highest acreage in the state. They represent 70% of the state's total cropland acreage and 40% of the economic values. Emission factors varied between and within crops due to variabilities in soil, weather, and management practices. Most deviated significantly from the default emission factor of 1.1% that the IPCC uses. Not surprisingly, given the diversity of California ecological conditions and management practices, we're going to have a lot of varied emission factors that range from 0.12 from rice to 12 for alfalfa. High emission factor in alfalfa was due to biological nitrogen fixation from the atmosphere, which can add over 300 kilograms of additional nitrogen per hectare per year in the soil. This wide range of changes in emission factors indicates that using a process-based model for N2O emission estimates is probably a better approach than using emission factors to estimate emissions at this scale. So during the 2011 to 2013 period, ARB sponsored the development of a process-based model called DNDC, which stands for Denitrification Decomposition. and it's specifically used for simulating carbon and nitrogen cycling in agroecosystems. The model accepts inputs defining detailed features of an agroecosystem. The model takes these data and translates them into 3 basic parameters that are that dictate nitrification, denitrification, and decomposition. The model outputs include daily changes in nitrogen and carbon speciation and concentrations of each species. The model is calibrated and validated using field measurements. The results indicate that DNDC is applicable for all the tested crop systems across the state. This figure is from the final report of our baseline modeling project. It shows the correlation between modeled and measured N2O emissions. In all, we had a total of 40 site year data sets from 4 research groups for 9 crops. DNDC performed very well in capturing the variation of N2O emissions from the crops under different ecological conditions. It actually performed better than another model that you probably heard of called Descent. They are different models and they both have their own advantages and disadvantages, but we've been working with DNDC. I just want to note that the highest flux out at the upper right side of the graph is not an outlier. It was an observed flux from a 5-year alfalfa field. And it just really represents the wide range in which the DNDC model can accurately predict emissions. We've used DNDC to develop the rice offset protocol, which was adopted by ARB last June. DNDC was the only accepted methodology for the GHG accounting in the rice protocol. We have used DNDC to estimate N2O emissions from ag soils at the county level. A lot of effort has gone into this, including collecting California activity data, calibrating and validating the DNDC model. We are running the model right now to develop the statewide emission estimate, and we'll compare the results with those obtained from emission factors to evaluate whether DNDC can improve the California inventory. DNDC can also be used to identify mitigation measures for GHG emissions and used as a tool for assessing the impact of alternative management practices on N2O mitigation at the field, county, or state level. N2O mitigation measures fall into 4 farming practices: fertilization, irrigation, tillage, and cover crops. The DNDC model now has built-in parameters for all of these mitigation practices, and we have finished parameterizing most of them in the current working model thanks to this project. And I will leave the discussion of the results to Dr. Berger. And I just wanted to talk about the ongoing and new research under the N2O research program. So we have a project using DNDC to quantify ag mitigation strategies, and that will be finishing up in the fall of 2017. The on-road motor vehicle emission research that I mentioned is also ongoing. We'll finish up next year. And also I mentioned the ambient monitoring that we're doing at JPL, and they're starting flights, I believe, in the fall. And we will complement that with our mobile monitoring platform sampling. And then in the fall, a project will begin to improve the emission estimates from manure management. I will now turn over the podium to Dr. Berger. He will share with us the results of the mitigation study. Dr. Berger is a project scientist in the Department of Land, Air, and Water Resources at UC Davis. Best department. He has been engaged in soil ecological studies related to nitrogen and soil water management for the past 15 years. Dr. Berger's work has provided critical information for our understanding of nitrous oxide emissions in several major California cropping systems, and will serve as a foundation for us to further develop mitigation strategies to reduce N2O emissions from California croplands. So let's welcome Dr. Berger. Thank you.
Good afternoon, everybody. In 2012, we obtained this contract from ARB to conduct research on mitigation options to reduce the emissions of nitrous oxide from agricultural soil. And we were then able to leverage this contract and obtain additional funding from the US Department of Agriculture in the form of a NIFA grant. And also we received some funding to do a nitrogen rate trial in corn from CDFA FREP. And because all these studies were on mitigation of nitrous oxide emissions, I'm going to present the results of all these studies in today's talk. So first, I wanted to give you some background on the rationale for our research approach and discuss the sources and pathways of N2O production in soil. And then I will go over in some detail over the field experiments that were conducted in various cropping systems, 7 in total. And towards the end, I have a summary of the N2O, of the potential mitigation with these different practices. And my conclusions will also include some economic considerations. And I also want to introduce a couple of web-based resources for growers and consultants that are geared to better understand N2O emissions and potential measures they can do to reduce the emissions. It was very clear from the beginning that we would focus on nitrogen fertilizer and irrigation management. There's a very strong correlation between nitrous oxide emissions and fertilizer N rates. The evidence is overwhelming from hundreds of studies, actually thousands, more than 1,000 in the whole world. And irrigation is so central to California agriculture. Soil moisture regulates the microbial activity that is responsible for producing these emissions, for producing the nitrous oxide in the soil. So there were 2 observations here that were instrumental. First of all, most nitrogen fertilizers are in the ammonia form, are ammonia-based, and therefore we can assume that they would induce high rates of nitrification, the conversion of ammonium to nitrate. And we know from that in temperate climates, nitrification proceeds very rapidly. If ammonium is applied to soil within a few weeks, maybe 2 weeks, most of it will be converted to nitrate. I've also observed in the literature that many reports from field experiments, they showed that most of a season's nitrous oxide emissions occur within the first few weeks, within maybe 1 month of the fertilizer application. And so clearly there might be a link there between nitrification rates and nitrous oxide emissions. And this has guided some of our approach to this research, but it was clear that we needed to understand the mechanisms of N2O better. In the 1980s, I think Mary Firestone and Eric Davidson from UC Berkeley, they came up with this leaky pipe theory. That is a conceptual model of nitrous oxide production and emissions. It basically just shows it's based on nitrogen transformation. So ammonium is added to the soil, or if it's mineralized, it goes through this nitrification pipe to produce nitrate. And in the process, some N2O is emitted, and then under anaerobic conditions, nitrate is reduced to nitrogen, atmospheric nitrogen, and during this process also nitrous oxide is produced. So since then, and actually also before, since this conceptual model was published, some more detailed work has been done and was done earlier also. And much of this work was in pure culture studies that provided actually some great breakthroughs. So this is showing again the nitrogen transformations. And the nitrification, there are 2 steps during nitrification, and they are carried out by different types of organisms, different microorganisms. So the first step is from ammonium to hydroxylamine and nitrite, and the second that is carried out by another group is the nitrite oxidation to nitrate. Then the denitrification that occurs under anaerobic conditions, that can be done by many different types of microbes. There are facultative and obligate anaerobes. And what's interesting is that nitrous oxide is an obligate intermediate in this process. So the leaky pipe model there is quite apt to describe this. But for the ammonia oxidation, I should maybe say that, point out that anaerobic conditions means instead of oxygen, the microbes use nitrate as electron acceptor. So in the ammonia oxidation, there is no substitute. The oxygen is really required for that first step. And then some nitrous oxide is produced mostly by abiotic reactions from hydroxylamine, but we can never measure that because it's so fast converted. And then, so these same microorganisms that oxidize ammonium, they can also reduce nitrate under low oxygen conditions. So low oxygen conditions, the nitrite, that becomes the substrate for N2O emissions. And because the first step is an aerobic step, oxygen is retired for that, it was often assumed that nitrification as source of N2O is mainly in dry soil and or just slightly moist soil, and that the majority of the emissions would be from denitrification when the soil was really anaerobic and denitrification would take place. So that was right, but not quite. So we wanted to know a little bit, how the oxygen regulates these different processes. And we showed that under low oxygen levels, that's to say 1 or 2 or 3% oxygen in the soil, the microbes produced N2O mostly during nitrification and also some in the denitrification process. And then when the soil went completely anaerobic, there was only denitrification, and not only that, but the rates of N2O production went up by an order of magnitude. So these insights really became good guidance to formulate our hypothesis, where we would target our mitigation practices. So it was, we then hypothesized that if we target managing the ammonium, the fertilizer fertilizer, ammonium, and oxygen, that this would have the biggest chance of coming up with some useful mitigation measures. So we can control nitrification by using inhibitors to slow down ammonia oxidation. Another way would be to avoid or use less pure ammonia fertilizers rather than and rather use mixtures. And the choice or the concentration of fertilizer, that could also influence the emissions. We know, for example, from field experiments that have been published that anhydrous ammonia usually causes higher N2O emissions than other N fertilizer, and that's a very highly concentrated form of ammonia. And when ammonia is concentrated, it increases locally the soil pH, and that in turn increases nitrification rates, which then might lead to additional nitrite sitting around, which becomes the substrate for N2O emissions. And then something what's not really often talked about is that the ammonia oxidation process itself consumes oxygen. That may not be much in the bulk of the soil, but locally where that ammonium is concentrated, this could actually contribute to lowering the oxygen levels and also stimulate emissions. But the other part, how do we manage oxygen? What can we do there? That is much hard. That is not so simple. That is because there's so many factors involved. It's very obviously we can avoid waterlogging, but farmers never want waterlogging anyway because plants would suffer. But then drip irrigation, that is a very different concept from flood or furrow irrigation, especially subsurface drip irrigation, because typically water is added every day and it's only added to replace evapotranspiration. That's a very different concept from furrow or flood irrigation where we add water every week or every 10 days, completely saturate the soil from the top down and then let the plants use it up. So it's pretty clear that drip irrigation would keep more of the soil aerobic, and that should help in reducing the emissions. Additionally, we of course want to maintain good soil porosity, good soil structure, so the soils can drain easily and oxygen can diffuse into the soil from the atmosphere. That would also help keeping the soils aerobic. So for our field experiment, we tested different nitrogen formulations and nitrification inhibitors in several systems in corn, tomato, wheat, and almonds. And then we also experimented with fertilizer placement. That was done in a corn system, and we evaluated drip irrigation, specifically subsurface drip irrigation in corn and alfalfa, and then a special kind of surface irrigation in lettuce. I'll explain later about that. We also had an organic treatment in tomato. And finally, we looked at how cover crops influence nitrous oxide emissions. This was done in a vineyard. So our experiments on evaluating these fertilizer N sources and nitrification inhibitors were, for the first year, they were done at a research site at UC Davis. And we used 3 different fertilizers with a varied ammonia to nitrate composition. So we had aqua ammonia, pure ammonia fertilizer, then a very popular type of fertilizer, urea ammonium nitrate, liquid, and then also calcium nitrate, so just purely nitrate. And we tested 2 urease and nitrification inhibitors. The active ingredients of the nitrification inhibitor were DNDC, dicyandiamide, and the trade name was this Agrotane Plus. So for all our field measurements, we used the static chamber technique. So a chamber is placed on the soil surface, and then at exact time intervals, air samples are removed from that chamber, and then from the rate of change of the gas that we analyze, we can calculate a rate. So for the corn, it took us a while to figure out how to place these chambers, because in a furrow irrigated system, there are different moisture levels and also different nitrogen concentrations. And we actually ended up using 3 different locations, one on the bed and then one at the shoulder. The shoulder is the distance from the edge of the bed to the furrow and in the furrows. And that way we could cover all the spatial areas where there could be emissions. The results were very clear. As we had hypothesized, the fertilizer with the highest ammonia content, the aqua ammonia, they had the highest emission. Then the urea ammonium nitrate, that was intermediate, and the calcium nitrate, the calcium nitrate had the lowest emission, and in fact, those were not different from the control that did not receive any fertilizer. So this was strong, pretty good evidence that the majority of emissions came from was nitrous oxide from nitrification. Of the 2 nitrification inhibitors, the Agrotane Plus, that seemed to work well because the would be the treatment where we added it to the urea ammonium nitrate, and it also reduced the emissions to the level of the control treatment. The other nitrification inhibitor, the G77, that was a reacted form that was supposed to have a different charge, and we had hypothesized that it would work better by not diffusing through the soil. But that was actually not the case. We got somewhat variable responses here, and it seems that this is not a good choice to use that nitrification inhibitor. So we then continued our experiments with nitrification inhibitors for 2 years in a commercial cornfield in the Stockton area. And there we also had other treatments. We had the N-rate trial, and we had 2 different fertilizer placements. And luckily, this grower also had actually a subsurface drip irrigated cornfield in both of the years. Even though it was not exactly part of the same experimental setup, but that field was in the same soil type, on the same farm, grown at the same time, and it was right adjacent. So I think the comparison is still a valid comparison. So for the nitrogen placement experiments, we chose to use either a band, apply all the fertilizer in one band, that's shown on the left side, or the same amount of fertilizer placed in 2 bands of either side of the corn plants. This is also shown on the picture. You see the injector there. The 2-band method is more common among farmers, but we wanted to show in principle what concentrating the fertilizer does to the emissions. So the emissions from the 1-band treatment, those are shown in red with the red symbols and the red lines. And the emissions from the more standard, the 2-band treatment, are shown as the darker line. And the blue lines are the irrigation events. You can see that the 1-band treatment had emissions that were higher. There were much larger peaks, and also the peaks continued throughout the entire season almost. Whereas in the standard treatment, the two-band treatment, there was a second peak with the second irrigation, and then it was over for the fluxes, and most of it was just near background levels. So that seems to show that concentrating the fertilizer, a high amount of fertilizer, increases the emissions disproportionately. We also had additional evidence that this was most likely because of the high of nitrate levels in the soil. As I've explained at the beginning, that if with very high nitrification rates, we sometimes get this buildup of nitrite, and that was exactly what happened. Both these one-band treatments, the open symbols, the open triangles and the yellow symbols, these were elevated nitrite concentrations in the soil compared to the other treatments. They were much lower. They were only slightly elevated with the first irrigation. So comparing the emissions, the seasonal emissions in all the treatments, by far the highest were these one-band treatments in both years on the left side, and then the lowest emissions were from the subsurface drip irrigation treatment. In the second year, there was actually a reduction of 95% compared to the standard treatment, which is shown as the blue bars. These are the grower standard fertilizer rate. The nitrification inhibitor, they worked only in 1 year. In the second year, there was a reduction by 60 or 70%. In the first year, there was no difference whether with the nitrification inhibitor. And we think that is because in that year, the fertilizer and the inhibitors were applied very early. The plants were only 4 inches tall. And by the time these plants were big enough to take up a substantial amount of ammonium, the inhibitor was already expired. They're only effective for about 4 weeks. And so it's one of a key. It's key that they are applied as late as possible so the plants have a chance to take up ammonium. If that is not the case, then it will just sit around, and when it is expired, it will again nitrify and produce nitrous oxide emissions. It's interesting that these mitigation measures and the nitrogen fertilizer placement method, they're bracketing the N rate, so they have a big impact on nitrous oxide emissions, almost the same or larger as varying the nitrogen fertilizer rates. They fell in between these two extremes. Okay, so now I'm switching gear now and talking about alfalfa. You have seen in the introduction that previously we had measured very high emissions from alfalfa systems. They are typically flood irrigated. They have traditionally been flood irrigated. And so since a few years, researchers and commercial companies are working on installing drip irrigation for alfalfa. For the growers, it's mainly for the potential yield increases. And the biggest problem is actually the wildlife. The gophers, they really like alfalfa roots, and they in the process of chewing these roots, they also chew up the drip tape. We tried to do this research for 3 years. In the first year, we had it on a research plot at UC Davis, a nice, completely randomized block design. And the gophers, they they chewed up the drip tape and we had to rip it all out. So, and the second year we went to a grower field and he had the same problem, and about halfway through the season he started to flood irrigate the field to chase off the gophers. And then finally, last year, we were able to do this. And the graduate student, Ryan Burns, he was able to show how the difference between flood irrigation and drip irrigation in alfalfa. So the peaks, the sharp peaks that you see, they're kind of small symbols. Peaks, they're flood irrigation events when nitrous oxide emissions were elevated. And then the open symbols, those are is the drip irrigation. There was basically no emissions whatsoever from the drip. So this was now a field that was irrigated like in a research plot. There was, evapotranspiration was replaced every day, so there was never a buildup of large moisture reservoir. And cumulatively, they're shown on the right. The brown section, that's during the growing season, so flood irrigation much higher and almost non-existent in the drip. But then during the rainy season in the winter, the emissions were similar in the two treatments. This is not so surprising. So I'd also like to point out that here in this field, this was a 2-year-old alfalfa stand and we had less than a kilogram for the whole year. And compared to the earlier study where we had 2 kilograms for a younger field and 5 kilograms for a 5-year-old field. So these emissions are indeed quite variable, as Sarah pointed out. We also looked at a different irrigation method in lettuce. So lettuce is typically either sprinkler irrigated, or sometimes growers use sprinkler irrigation to bring up to germinate the crop, to bring it up, and then after thinning they roll out a drip tape as surface drip. That's shown on the right in the bottom picture. And then for the remainder of the season, the crop is irrigated with surface drip, and also fertilizer is applied through the drip to the drip lines. And we hypothesized that the combination of sprinkler and drip that would lead to lower emissions. The results were sort of inconclusive. I want you to focus on the one on the right side. So in 1 year, there were indeed, in the second year, there were indeed lower emissions with the sprinkler drip combination, but in the first year, there were very high emissions and there was no difference. And this was done on farm, and we could not control everything on this on-farm study. And from the fertilizer applications, they were much too high in the first year, much more than 300 kilograms per hectare. And we had shown in our first ARB contract work that with 170 kilograms of N, that's shown on the left side, the middle treatment here, that was plenty of fertilizer, and there was no yield increase at higher rates. And also this shows the crop nitrogen that is taken off by the crop. That was kind of reasonable, 170 and 136. And then with the higher rates, there was not much more nitrogen was removed by the crop. So it seems like in this industry, what is needed is much better controls on both the irrigation and the fertilizer. And there is, UC Extension actually has a program now. It's called Crop Manage. It's a management model. And I went to their workshops, and there's quite a few growers have signed up for it, and they're using it, and it helps them to decide how much water and how much nitrogen to apply. So I'm going back now to the nitrification inhibitors, because we tested them in field experiments in tomato and wheat and almonds. In tomato, it was drip irrigated, and in wheat, that is an entirely different system. That's grown in the winter. It's rain-fed. And almonds, these were micro sprinklers and the fertilizer, and inhibitor was applied through the micro sprinkler system. So we cannot predict the weather, and we had the luck that we actually did these trials in 2 drought years. I'm just going to show the results from the second year. In that year, there was no rain. Maybe I should back up a little bit. Wheat is usually planted in November, and about half the fertilizer is applied at planting, and then the other half is applied in February. Often it's flown on by plane as a top dress. So in that year, there was no rain, and the crop wasn't established, and in January, the grower decided to flood irrigate the field to bring up the crop. And then only in late February, it started to rain in that year. And this is shown here on the right. This is our tarps show we had various treatments, and we didn't want the plane to put fertilizer in our treatments, of course. And so from then on, it rained very, very good, and actually turned out to be a really good crop year. That if you could get the crop established. That fertilizer that was applied in November was sitting around in the soil, and when the grower applied his flood irrigation, then we got this really large peak. It's shown here, and it was about 0.5 kilogram of N2O per hectare. And then our treatment, we had several treatments here for this top dress application just before it started to rain. One of them was Super U, that's similar to that Agrotane, but it's for granular fertilizer. It has an inhibitor in it and a urease inhibitor. And then we also tested nitropyrin, which will be on the market this year or next year in California. And we also had a slow release fertilizer. It's a sulfur-coated fertilizer, and that is actually, the growers have some interest in it, because it's releasing, it's not an inhibitor, it's just releasing the fertilizer slowly over time. And I know several growers who tried it out because they were hoping for better yields and better nitrogen use efficiency. So as I said, in that year was a good, this crop turned out very well. It had very high yields. And we had labeled some of our fertilizers with stable isotopes, and we were able to show that about 75% of this fertilizer ended up in the crop. So that's a pretty high recovery, and there was no difference regardless of what the treatment was. But going back to these emissions from the top dress, that Super U and the slow release fertilizer, they performed really well. Had lower emissions than the urea. In tomato, we compared, we were also on 3 commercial farms, or 2 commercial farms and 3 different fields. One was in 2 different years, I should say. So we had an inhibitor. The results of the emissions are shown, the red bars, these are the emissions from the inhibitors, and then the control treatment, the black bars. That was in the conventional drip irrigated system. The difference between using this emitter or not, inhibitor or not, was not very large. In the second year it was a significant difference, but it's a very small difference. We also had an organic treatment in tomato, and that was traditionally furrow irrigated. It works better with organic production, and it had higher emissions, more than twice as much. But what I also want to point out here is that in the lower graph, we converted the nitrous oxide emissions into CO2 equivalents, and the brown section of these bars are the N2O emissions. And the other sections are other greenhouse gases associated with production. There's fuel for tractors, irrigation, fertilizer. And so the difference between using an inhibitor or not are quite small when all the greenhouse gases are considered. I didn't have a slide of the almond orchard because those emissions, we tried this for 2 years, those emissions were very low, regardless of whether using an inhibitor or not, and we got absolutely no reduction. Finally, in the vineyard, some of this work is still going on. We wanted to look at the effect of cover crops. So a couple of years ago, a study was published that showed high emissions from a cover crop that had been incorporated in the spring, and then the fields were left to sit around, and then with the first rainfall in the next fall, they had extremely high emissions. And so we wanted to look at the different types of cover crops, whether it mattered, whether it was a legume or a grain cover crop. And that's what these treatments were. They were legumes, mixtures of grasses and legumes, and pure rye cover crop. In one of the 2 years, we had substantial emissions with the first rainfall, and it seemed that indeed the cover crops, they increased the emissions a little bit, but there was no difference between the type of cover crop. This research is still going on because we are interested how organic matter inputs, what kind of an impact that they have on the emissions, because the carbon levels, that can also drive oxygen levels in the soil. So I put this summary together from all our results from these experiments, and I converted all the N2O emissions into CO2 equivalents. I thought it would be more illustrative to see the differences. And for the nitrification inhibitors, I think we can say that it was quite variable, the response. They seem to work well in the corn in 2 of the 3 applications, and because probably the fertilizer anti-inhibitor is applied at one time at a certain location, and we got between 300 kilograms and 1.2 tons of CO2 reduction. And now compare that to the tomato work that was in drip irrigated tomato. The reduction was very small, less than 100 kilos per hectare. In wheat, also not very large, was intermediate, but there is definitely some promise there. And what's encouraging is that growers are actually interested, they might be interested to use one of these inhibitors or slow release fertilizers because they hope for some small yield increase. And almond, I've already said we couldn't get any reduction. So subsurface drip irrigation versus furrow irrigation or flood irrigation, that clearly reduced the emissions in all the systems. Some of these results, or most of these, are from the present research, and some were from previous research that is either already published or was in a previous contract. And so in tomato, the adoption of drip by the tomato industry, that has reduced the emissions by about 0.5 ton per hectare. And in alfalfa, the reduction was not so large in this experiment, but it was clear. And I also included the lettuce sprinkler drip combination, even though the results there were only valid for 1 year, or they worked only in 1 year, but it was similar to the reduction in alfalfa. The fertilizer formulation showed that anhydrous ammonia lowered emissions by 300 kilograms of CO2. This was shown in a study that's already published in wheat. And the aqua ammonia had higher emissions than UAN. That is from this experiment. The most drastic reduction was going from a one-band application of UAN to a two-band application in the corn system. So this is, of course, just an isolated study. We just have this one experiment. But I think we proved in principle that it's not a good idea to concentrate fertilizer spatially. There is some published research that has shown this with other fertilizers. They have compared broadcast urea with banded urea, and they have similar results, although not nearly as dramatic as we had it here. And to put this all in perspective, I also wanted to include nitrogen rates, the reductions we can achieve by using the recommended fertilizer rate versus an excessive nitrogen rate. And with excessive, I mean, in this case, I compared a rate that was about twice as much as the recommended rate. And of course, this is still very important because if farmers apply an excessive rate, then you can guarantee that these emissions go way up. So the main conclusions are, or the main findings are that the most reliable way to reduce the emissions would be by switching to subsurface drip irrigation. However, this will probably, it may not be optimal for every system. We cannot irrigate all ag systems with drip. And mainly it's a very big investment, and it works only for high value crops. I'll show you the economics in the next slide. And regarding the nitrification inhibitors, I think what's important here is that we cannot recommend using them just like that. There is also some know-how required of when to apply it. It's important that they're applied at the right time. And what's not so encouraging is that in none of these experiments did we see a difference in use efficiency or yield. And for growers to spend the extra money for the nitrification inhibitor, they would want to see that. But we were not able to show it in any of these experiments. And obviously, spatially concentrating the fertilizer is not recommended. And the same goes for these concentrated ammonia forms, because they lead to higher emissions than the more the mixed formulations. So the UC Extension has for decades promoted more soil sampling, and if farmers can use the recommended rates, the recommended fertilizer rates, but they have to take into account the residual nitrate that's already there. And so to sample a large commercial field, it would cost maybe several $100s for a grower. But if he could then reduce the nitrogen rate, that he could easily recoup that money. So the savings from the fertilizer, because I calculated it would cost him only about $10 an acre. And it can be done. We published a study last year in California Agriculture. We published a protocol how to reliably measure nitrate in drip irrigated tomato fields. Regarding this installing the drip irrigation, so I have some numbers from a study that came out last year. So if the installation costs of the drip system are amortized over the life of the drip system, then the operating costs are about $2,700 per acre. So right now that's still very favorable for tomato because the price of tomato is good. but production costs are already $62 per ton of tomatoes. So it will only work for high-value crop, as I said before. And these nitrification inhibitors, they cost about $50 per hectare. And right now, price of a ton of CO2 is worth only $12.69 on the free market, on the carbon market. So as long as the price of CO2 is still so low, it's not economically, it doesn't make economic sense to use it just to reduce the nitrous oxide emissions. So the farmers need to, either that has to be subsidized or some other incentive for them to use nitrification inhibitors, because we have not been able, and there are actually very few studies that have been able to show yield increases. Before I take questions, I would also like to introduce two resources. This one it can easily be found by Googling the Solution Center for Nutrient Management. It's a UC Serap site, and all our greenhouse gas research results are there. There's a big database, and published studies have been summarized and translated into lay language. So it's a good source of information that has specifically information about greenhouse gas emissions in agriculture. And the other side would be the California Fertilization Guidelines. It has all the information about the rates for the many different crops, and they're constantly adding new crops. This is CDFA FREP. And there is also a big database with all the studies where these recommendations are based on. Both of these sites, they're pretty actively used. They receive about 7,000 hits per year. So it's not huge, but they are being used. And I'd like to thank again our funding sources, and also acknowledge the collaborators, the PIs and the graduate students on the left side, and especially also the growers. There were 6 growers that offered their land where we could do the experiments, and then many students and technicians that helped with the measurements. Thank you very much.
Does this work? Oh, okay.
There you go.
Okay.
Talk into it.
Okay. So thank you. That was a great presentation and very thorough, and has a lot of really useful information for the agency and the state. We have a couple questions from the internet, but I wanted to start with questions in the room. If there are any.
Let's take one from the internet.
We'll just take this one first.
Earlier, you mentioned that the DNDC was calibrated for rice. Is that for methane specifically or nitrous oxide?
Yeah, for both.
Are you using a different version? Sorry. Are you using a different version than the one that's in the compliance protocol?
So the one for the offset protocol was, specifically used for, created for the offset protocol by the staff in the offset group. So, it's the same DNDC model, but with a more user-friendly interface.
Question, sorry. For Dr. Berger, I'm sorry if I missed this, but did you say that there's also a water savings associated with subsurface irrigation? And if so, then what's the ROI period on the investment for installation?
Yes, there are water savings. because there's no, the evaporation factor falls away, so that's about 3 or 4 inches of water. And well, the applied water is much less on the drip irrigation, but the applied water in furrow irrigation that usually flows to another field and is used in California. So the absolute water use is not so much less. What was the other? The
Subsurface.
State it again.
the payback. I think usually you do it for about 6 or 7 years. But some systems are in place longer, but for the economic calculation, I think it's 6 or 7 years, yeah.
We're just going to take one quick question from the internet. This is from Darrell Generette from UC Riverside. Recent data from a field study of sorghum in Imperial County during the summer showed soil NOx emissions at the highest levels ever reported, up to 900 nanograms of nitrogen per meter squared per second. Would you expect a corresponding high nitrous oxide emission in Southern California or in response to future warming? And if so, can you discuss how high temperature conditions may differentially influence processes from ammonia oxidation to denitrification? Second, can you comment on potential mitigation of N2O in such hot environments? So I guess there were really 3 questions. So if you see high NOx, will you see high N2O? And then will higher temperatures impact nitrification and denitrification and potentially affect them differently? And then in those high temperature environments, what are the potential mitigation strategies?
So yes, we also have measured NOx emissions. And overall, we found no correlation between NOx and N2O. But NOx is strongly correlated to nitrification rates. And also, the highest rates of NOx emissions are immediately after fertilizer applications. So it's clearly a response in response to fertilizer. You would expect that you would also see high N2O, but we did not show this. And I think it's because the NOx is highly reactive. It will react to NO2 and react to produce ozone if it's on the surface, and whereas nitrous oxide is more produced slightly below the surface in the soil where there is no oxygen. And so that's as far as the correlations go. And then as temperatures increase, there is more, probably both more NOx and for sure more N2O, because microbial processes, they're temperature related, they have high, they just increase with increasing temperature. But I should also say that we, for example, measured in the NOx when temperatures reached 40 degrees Celsius in the field, the emissions wouldn't go up anymore, because at this temperature, some microbes are inhibited if they're on the surface. So right, and then how are denitrification and nitrification related at high temperatures? So if you have denitrification conditions, that means that usually the soils would be saturated with water, and then they're actually much cooler than slightly drier soils. So But definitely, if we have increasing warming, overall the emission rates would go up. Yeah.
There's just a question in the back.
Yeah, the correlation of increased nitrous oxide due to moisture. Was the driver for flood irrigation versus subsurface drip irrigation a function of the concentration levels in the water itself? Was that measured at all so that you could draw an irrigation factor in the irrigation, not just the methodology, but the concentration that was in the water itself?
So are you talking about the concentration of inorganic nitrogen in the water?
Yes.
No, I don't think that is well,
That's okay. If it's not measured, that's an answer that maybe can be researched later, because obviously the moisture for increased oxygen levels is a trigger for.
Right.
But my question is that the flood irrigation versus subsurface drip irrigation, is it just the methodology that's causing the reduction or the increase, or might it be the higher levels of concentration of nitrogen in the water itself, so that you're flooding with high levels of nitrates versus lower volumes in drip irrigation? Mm-hmm. There could be two triggers.
Okay, yeah. Well, I think, but the main driver will be the oxygen, how the water influences the oxygen level in the soil, and not so much the concentration of nitrate, because we have the high emissions we have from fertilizer, and those concentrations in the soil, they are much, much higher than the concentrations of nitrogen in irrigation water, even if it's high. So I think it's not driven by the nitrogen in the water. But during fertigation, of course, the concentration is really high.
Yeah, and it becomes an issue from a leaching perspective because it's a media that's carrying down beyond the vadose zone. And that's why from a water perspective, a water quality protection perspective, we're drawing that correlation of including the concentration of nitrates in the irrigation water to the overall mass balance of the nitrogen cycle.
Oh, yes, of course.
Wasn't sure if it was the same
that
correlation.
That should actually be part, I didn't say that, but when I talked about soil sampling, also the farmers have to know how much is in the irrigation water and adjust the fertilizer rates according to that.
Correct, yep.
Very important, yes.
Thank you.
Martin, I have two questions. First, those nitrification inhibitors, they don't seem so promising because they're expensive, there's no yield effects, and it seems like even if it was subsidized, you would still have to make sure they are used exactly in the right condition to have an effect. So my question is that, would you agree with my assessment?
Yeah, there's a little bit of negative assessment, and maybe it also came across here from my talk like that, and that was not intended like that, because on the other hand, these studies and studies in the literature have shown pretty good reduction potential for nitrification inhibitors, and so I think we should focus on that and maybe think of creative ways of using them.
And my other question is that you've shown like very, very large reduction of emission when you use something like calcium nitrate rather than the ammonia. So and you didn't talk about the economics of that. So what's the potential to shift from ammonia to something like calcium nitrate?
Oh, that's a good question, yeah. I should have said that. So the calcium nitrate treatment was in there because we wanted to show that indeed nitrification is the main source of N2O, even in even in furrow irrigated systems. And so that was a perfect control. That's actually the same control that John Bremner used when he first showed that 1978. And but if we switch to nitrate fertilizer, we first have a water issue because people will think, and I think it's true, that it's more mobile, immediately mobile, and the crops take up no ammonium, so that I think we cannot. And the second part is that producing nitrate fertilizer has a very inherent, it's expensive and it has a very inherent high energy cost embedded in it. Because to make nitrate fertilizer, we have to fix it the same way as ammonia fertilizers, but then you have to react it with acids. And I've looked at these numbers. It's very disadvantageous if you look at the whole life cycle of fertilizer production. So I didn't want to go there. It's just, yeah. So it's not recommended. Mm.
We're going to take another question from the web. Thank you. This is from Tyler Smith. Thank you for an informative presentation. On slide 6, it was mentioned that under low oxygen conditions, nitrous oxide is produced during nitrification and denitrification, while under aerobic conditions, nitrous oxide is produced only during denitrification, but at a much higher rate. Which conditions result in higher nitrous oxide emissions overall, and by how much?
So if there are denitrification conditions, then it will produce much higher emissions of N2O. In our controlled study, the rates were about 10 times higher when there was no oxygen and it was just denitrification. Yeah, I know I know the question. This one, yeah. Okay.
Great. Are there any other questions in the room? Thank you.
I'm wondering if the same kind of nitrogen fertilizer was used for the organic crop cases?
On the organic farm, it was a totally different management. They used cover crops, legume cover crops, and chicken manure, composted chicken manure. And they also applied some guano, not very much, but about 30 kilograms N per hectare.
Did that affect the N2O emissions?
Yeah, that also affected the N2O emissions in a sense, but that we also in that system, we measured higher emissions at the beginning of the season with the first couple of irrigations, then later on. But the higher emissions were also due because it was furrow irrigated.
So what I'm hearing is that the furrow irrigation swamped any positive or N2O reductions that you might have gotten with organic fertilizer?
Yeah, I think I agree with you.
Okay.
Yeah. Mm-hmm.
We're going to take another question from the internet. This is also from Tyler Smith. In addition, has the reduction of nitrous oxide emissions with two-band application versus one-band application been demonstrated in other crops in addition to corn?
I have not seen in the literature this exact combination that we did with a two-band urea ammonium nitrate versus one-band urea ammonium nitrate, but there have been some studies of comparing broadcast with banded fertilizer applications. So that's maybe the closest comparison.
I had a quick question. So very impressive talk, very comprehensive research. Are you aware of any other jurisdiction, either the U.S. or another country, that's one, researching this topic, and two, are there any active mitigation programs anywhere in the world?
I'm not sure about that. I would think so. There are some, but I would have to research that. Yeah, sorry.
All right, we're going to take another question from the internet. My question is around the nitrous oxide emissions corresponding to the various mitigation practices for corn. Were the emissions normalized against yield? Were changes in yield seen between the treatments?
So the emissions were not normalized to yield, and we have, in most systems, we have the yield data, but my talk, it was just getting too long and too big to include all that. But by and large, I'm glad that you're asking this question, because by and large, we found not really big yield differences among the treatments. Even in our N-rate trial, we saw a little bit higher concentration in the plants, but basically the yield was not, they were not different. And so it means that all these fields were probably quite fertile and maybe could have used a little bit less fertilizer.
Are there any other questions in the room? Okay, I'm just going to take one last question from the internet. What are the cost differences between different fertilizer types? In Almond, you saw the same trend that can produce less in nitrous oxide than your urease, what is UAN? Less NTO than UAN, but costs substantially more with no difference to tree health. Can you explain the nitrification inhibitors, nitrogen release, and length of time the inhibitors work? He also had a comment, soil sampling is not appropriate for tree crops. They use leaf sampling to assess nitrogen status.
Yeah, there's quite a number of questions, and but I know about the study. And the first one, what are the cost difference between different fertilizer types? I actually wanted to include it here, but the fertilizer prices, they fluctuate so much. I didn't manage to get it's hard to keep track of fertilizer prices, how they change. In general, the fertilizers that are like anhydrous ammonia or urea, those are the cheapest ones because there's nothing else is done to them. And the mixed fertilizers are a little higher. So CAN 17 produced less N2O than UAN, but I think CAN 17 is mostly nitrate. It actually supports our research that nitrification is an important source of N2O. And I think also CAN 17, yes, is more expensive because it's a more involved process to produce nitrate fertilizer. And the nitrification inhibitors, okay, so we found in some lab studies and corroborations from field measurements that they last about, this Agrotane Plus, that lasted about 1 month in the field, and then the ammonium had disappeared. So it's during this time that less ammonium is released from these fertilizers and plants can take it up. And as temperature increase, the efficacy of the nitrification inhibitors decreases. So, but we have pretty high temperatures here, so that's about. Yes, of course. Soil sampling is more for field crops.
All right, well, thank you so much to everyone who came. Oh, we have one last question.
Sarah, if you could just give us a view of the future with the results of this study, what are ARB's next steps? Is it mostly for the inventory, or there are other
systems that could be affected by the results of this research.
Are you asking how the research results from this project will be used, or what are the next research projects we?
No, how the
Okay, yeah. Well, I mean, right now we're developing the scoping plan, so be used to inform many programs. I mean, yeah, all the programs looking to reduce nitrous oxide emissions. And as Martin said, you know, they were looking at other greenhouse gases as well, so that information will be useful too. So it will inform those programs, and, you know, from this research, we'll also identify research gaps to inform future research as well, so. But I mean, if you're asking, like, are we going to use this right now to, like, create an offset protocol? Like, no, but you know, it's, you know, furthering the development of all of our programs. All right. Well, thank you all for coming. I really appreciate it. And thank you, Martin, for giving a great presentation. And for those of you that tuned in online. All right. Thanks.